Good afternoon, everyone. Today we are very happy to have Juan Pedraza from University of Barcelona, and he will tell us about Lorentzian threads and holographic complexity. Juan, thank you very much, and take it away.
Okay, thanks for the introduction and thanks for the invitation to give this seminar. Yeah, so I'm gonna be telling you about these two papers that we put out earlier in the summer. This is in collaboration with Andy Spesco, which is a postdoc at University College London, Andrea Russo, who is a PhD student at the same institution, and Zach Wheeler-Davis, who is a former PhD student, now a postdoc at Perimeter. So I'm going to be telling you about holographic complexity, and in particular about the reformulation of one of the proposals, the complexity equals volume, in terms of Lorentzian threads. And this is analogous to the reformulation of Ryu and Takayanagi in terms of Riemannian bit threads, which I don't know if you have heard, but it was a proposal put forward a couple of years ago by Friedman and Hedrick. Okay, so just please stop me if you have any questions. This is my outline. I'm going to start with a very quick motivation of the problem, that why we started doing this investigation. Then I'm assuming that some of you are not very familiar with the standard bit threads. So we'll have a couple of slides to review it. Then I will present our reformulation of CB. Just present the prescription and explain some of the general properties. Then I move to the interpretation. And then I will present one application of this formalism that allows us to derive bulk Einstein's equation from the first law of complexity in this case. And finally, I will end up with some comments on CB in general, and why we think that something more general should be necessary for a generic situation. Time permitting, I will also show some of the ideas that we are still thinking about, that we think are interesting to explore. Okay, so the motivation. So, well, our work is in the context of holography and quantum information. In this context, entanglement entropy has already been proven to be a wonderful tool to understand the emergence of gravity. But as such, in this context, entanglement pointed out a couple of years ago, entanglement is not enough to describe all aspects of gravitational physics in the bulk. Okay, I was saying that, well, Susskind pointed out that entanglement is not enough to describe all aspects of gravitational bulk physics. And one example is that if you want to describe the growth of the wormhole inside of a two-sided black hole, then entanglement is not enough, because it doesn't describe the growth at sufficiently late times. In thinking of what possible dual of this growth would mean, what possible observable, he came up and suggested that maybe it is related to computational or quantum complexity. And in a few words, this quantity is defined as follows. So first, as probably most of you work on this, so you know the definition, but you first define a reference state, and then a target state, and then upon selecting a set of elementary gates or operations that you are allowed to act with, then complexity is given by the minimal number of such operations that you need to go from the reference to the target state up to a certain level of accuracy. So this is indeed the claim is that this is a good candidate to describe the late time growth of the wormhole, because even though in these situations entanglement can grow over a time scale that is at most polynomial in the number of degrees of freedom. Complexity can grow over a time scale that is much longer, that is exponential on the number of degrees of freedom. So that's why he proposed this one. So there are two main candidates for the holographic dual. I say two main because right now there are many other proposals. But well, it's fair to say that these are the two that are have been understood better in holography. So the first one is the complexity equals volume proposal. So in that case, first you fix a boundary Cauchy slice and you ask what is the maximal volume of a slice in the bulk that connects or that is anchored at this boundary slice. The second proposal is the complexity equals action that now relates complexity to the gravitational action evaluated at the Wheeler-DeWitt patch, again anchored at the same boundary Cauchy slice. Now, these two proposals share some of the qualitative properties. They both capture the latent growth of the wormhole. They both saturate the Lloyd's bound for the rate of growth. And they both capture what is called as the switch effect, that is how it reacts when you perturb the system, for example, sending shock waves. But what is worth emphasizing here is that a number of features are not so well understood. And some of them are the following. So it is not understood what the role of the reference state is in either of these proposals. It is not understood what are the set of gates that we are allowed to act with, and it's not understood. There is no first principle derivation using the tools of holography. So up to now, these are just conjectures for the dual of this quantity. And it's fair to say that it's not on equal footing as, for example, entanglement entropy, which has a proof using the path integral. So what our work does, and what I'm going to explain in this talk, is to define some progress towards understanding some of these points that are not well understood, at least in one of the proposals, that is the CV proposal. And we did it by reformulating it in terms of Lorentzian threads. And using this reformulation is that we can learn a little bit more about this proposal. So before moving to that, and so I'm aware that some of you are not familiar with bit threads. So I'm just going to have a few slides reminding you what they are and why they are useful in particular. So for that, let me just briefly introduce the RT prescription that probably you already all know. RT prescription is this formula that is useful to compute holographically entanglement entropy for a given boundary state and for a given sub region. And this formula has already taught us very important lessons in the context of holography. Most importantly, that it has given us the notion that geometry, and well, not only geometry but also the dynamics emerge from the laws of entanglement entropy. One of the features that is not it doesn't capture or is not clear from this proposal is how are the quantum bits encoded in this formula. So what are the quantum bits that this formula is counting? So one imagine that you may have is the formula for the black hole entropy that is given by the area of the horizon. In that case, the picture is that the bits are encoded at the horizon, or degrees of freedom living at the horizon. But if you try to extrapolate this picture to the context of holographic entanglement, something arises, an issue is that the RT surface is in general an imaginary surface, and in particular, it can jump discontinuously in certain situations. So it would be rather odd to assume that the quantum bits would have this discontinuous transition. One of these cases is where, just for example, when you have two disconnected systems, and depending on the relative separation between the sizes between these systems, you can have this transition from a connected to a disconnected configuration. And this is one of the cases where this puzzle arises. Likewise, the quantum information meanings and the properties of entanglement and quantities derived, such as mutual information and so on, are not so clear, and other properties such as inequalities, these two inequalities in particular, strong pseudo-additivity and monogamy of mutual information, it's not clear how it seems to appear on the same footing, as long as we are thinking of them in terms of RT surface. This is a kind of a conceptual puzzle, because we know that one of these two inequalities is the strong pseudo-additivity is satisfied in any quantum system, while the monogamy is not true always, and it's only in these holographic settings that is valid. So this reformulation of bit threads tries to answer some of these puzzles, and the reformulation is as follows. Instead of minimizing an area in the bulk, what you do is to introduce a new object that is a flow. The flow is a vector field that satisfies a number of properties. In particular, it's a divergence-less vector field, and this has a norm bound that is essentially upper bounded by the Planck length. And the reformulation relates essentially what it states in this formula is that the minimal area is given by the maximum flux, where now the flux is through the given boundary region. So one picture that maybe it can help clarify this this equivalence is you might think of a system in fluid dynamics, where and what you are trying to do is to maximizing the flow subject to some conditions at the boundaries, and then in that context, the maximal flow is given by the minimal cross section of your geometry, right? So this is the intuition here, and that's why the equivalence works out. Now the proof of this equivalence follows from what is called as the continuous version of the Max-Flow-Minkat theorem, and it can be proven more rigorously using convex optimization techniques. It was done in a follow-up paper by Matt and Veronica. What I want to point out here is that, or what I think is insightful about this reformulation, is that it provides us with a more fine-grained description of what this formula is computing. In particular, one of the properties that I told you about is that this divergence condition. This implies that essentially that there are no sources in the bulk for this vector field. Instead, all the integral lines, or the integral lines that we call also threads, all of these threads should start and end at the boundary, right? So these integral lines connect the boundary points or degrees of freedom that connecting points in the interior of the region of interest with points in the exterior. So if you think of the discrete version of this formula, I can think of these integral lines to have a finite thickness, and all that this formula is computing there then is is counting the number of of these bell pairs that I can distill from the state. So this is at least conceptually is a nice interpretation because it fits well with our intuition from quantum information. It also solves a number of conceptual puzzles. For example, in these situations where you have a transition, what happens is that these flows of the threads, they can be continuous. So there is no issue with these continuous jumps. And the properties and the definition of entanglement and derived quantities are more aligned to their quantum information meaning. To give you an example here, in this setup, in this figure, if you're interested in computing the mutual information between A and B, then all you need to do is to count the number of threads that are in this orange thread bundle. And this is nice because mutual information essentially counts the amount of mutual correlations between the two subsystems. So that's nice that we have this interpretation. Another solution that it provides is that now these inequalities that I said they were on equal footing from the RT perspective, they now come from different properties in the bulk. The first one comes from nesting, while the second one comes from the multi-commodity theorem. So it's nice that we can now distinguish between or have a notion of why they are different in the bulk. And finally, another property that I want to point out here is that these flows now, they are highly non-unique, but you can try to fix this uniqueness by just imposing some certain property. And it turns out that when we impose bulk locality, then a natural condition emerges to Einstein's equations. So this notion of that gravity or geometry emerges from entanglement has a natural realization in this language. Okay, so any questions so far?
Yeah, can I ask you a question?
Yes.
So it looks to me, I was thinking in this picture with threads, can I think of it as I put, say, positive charges on the boundary within this interval and then negative charges elsewhere? Then I have some kind of thread that looks like what you have drawn.
Yeah.
And in practice, or if I use some equations, like how can I do that? But then it looks like some Maxwell equation instead of Einstein equation in the curve space.
Yeah, so you can think of that in terms of charges, but it's not completely equivalent, and that's due to the norm bound condition. So in Maxwell's equations, you don't have any norm bound, while here you do have that norm bound. So that's in one sense in which this is not completely equivalent to Maxwell's equations. And yeah, so that's all I can say.
Okay, okay. Thanks.
Okay. Okay, so let me move to the now the complexity side of the story. So the first thing to notice is that this max flow min cut theorem that I told you about, that's a Riemannian theorem. So your manifold there is Riemannian, but there is also a Lorentzian analog that is called the Lorentzian mean flow max cut theorem that was also proven by Matt and Veronica in their paper. And using that Lorentzian version, then you can reformulate the maximal volume to a minimization of a flux. So this is not in some sense natural because the CV proposal is intuitively is very analogous to the RT prescription. So it was natural to conjecture that such reformulation in terms of flows exists. Now this reformulation was already put forward in this paper by Matt and Veronica, but our job here was to just push it forward and explore the properties, the interpretation, and so on. So a couple of distinctions between this and the Riemannian version is that, of course, as you can see here now, we have a minimization instead of maximization. The manifold here is Lorentzian, and these vector fields are now time-like instead of space-like. And finally, there is this bound that now it changes sign. So now there is a lower bound on the norm instead of a maximum bound. Now here I'm showing you two illustrations of how these flows look like. Something that is very important for this equivalence or even this theorem to work is that even though the manifold that we have here is Lorentzian, it should be compact. So in general, we would need to close the manifold by gluing Euclidean sections in the infinite past and the infinite future. And then I can write down what mean-flow max-cut theorem looks like and how to reformulate this in terms of classes. So the fact that we actually require this compact manifold, then it reminds us to a topic that is often discussed in ADS-CFT, that is the topic of state preparation. So in that context, what the problem that you are trying to solve is given a set of initial conditions in the infinite past, like if you define what your state is and what the sources that you are turning on, then you want to determine dynamically what is the state that you have at a given time. So what is the initial data that you are preparing? Another way to discuss the same problem is that you can alternatively define the state that you have in the infinite past. The infinite past in this here, it would be at one point in this Euclidean section. You define the state there, and you define the state on this slice, on this disk. And then you can ask the question about what sources do you need to turn on such that dynamically it brings your initial state to the final state. So this is nice because it in particular make use of this reference state. And just to give you an example, you can ask in this context, what would be the volume if the reference and target states are the same. So if both, say, if you take them to be the vacuum, then what happens is that you don't need to turn on any sources. And in this context, what happens is that you can collapse this Euclidean portion of the manifold to a point. Then if that happens, then the volume that you can fit is zero and the complexity is zero. So it is only when the reference and target states are different that actually the volume is non-zero. Okay, another nice interpretation of this reformulation is now that when you think of the discrete version, now the threads here, which I define it to be the integral lines, they are time-like instead of space-like. So they are now word lines that instead of connecting a pair of degrees of freedom on the same state, what the role now is to transport degrees of freedom or evolve them in time, right? And it is natural to interpret them as gates or as operations in such a way that this flux minimization now counts the minimal number of these gates or these operations that we need to bring my initial or reference state to the target. Finally, we can say a little bit about the tolerance. So again, if you think of this discretized version of the problem, then the threads will have a final cross section that is given by given in terms of this bound, and this cross section of the discrete threads they basically fix a resolution, a maximal resolution that I can set for an individual cell of volume, right? So that's my tolerance would be set by this thickness. There are a number of properties that follow from even from the definition of these Lorentzian flows, and most of them can be easily adapted from the Riemannian versions. Here I'm gonna just tell you about a couple of properties that I think are nice. One of them is the nesting property. The nesting property tells us that whenever you have two nested surfaces, in this case, I mean nested in time, then there should be at least a or at least one flow that simultaneously minimizes the flux through A and AB, right? So based on this property, then we can now think of more exotic. Not only have a reference and a target state, but we can also have an intermediate state, for example. So now I can ask, what is the minimal set of gates that brings me from one state to another, subject that it goes through an intermediate state of my choice. And based on that, we define this quantity that we called conditional complexity. That is essentially is the number of operations that I need to go from a state to another, subject to going to some intermediate state. And what is nice is that in terms of flow, this quantity has a very nice, very simple interpretation as the flux through the minimum flux through this extra region. Now, thinking about these nested situations, then we can also now think of considering a situation where they are only infinitesimally far apart, and in that case we can come up with using the PVC correspondence, which is a momentum volume complexity correspondence proposed by Susskind. We can come up with a natural candidate for one of these flows that do this simultaneous minimization. That is given in terms of the bulk stress tensor. And here, n is a normal vector, and this theta is a infalling or tangent vector, tangent to the surface sigma. What is nice here is that you can repeat this for 3 nested surfaces, and once we take again this limit of small delta t, then we arrive to an equation for the second derivative of complexity, which turns out to be proportional to the first derivative in momentum. So we can now connect this to or explain it in terms of flows, and this is a nice result. I think this is a proposal by Susskind that he was thinking that the Newton's law of gravitation might have an origin in complexity. There is a further property that I don't have time to talk about a lot, but I can just mention it, is the superadditivity of subregion complexity for CV. And here, subregion complexity is just a derived quantity that can be defined when you have a subdivision of the degrees of freedom of your boundary Cauchy slice. So in that case, I can ask what is the complexity of each of the subsets, and there is a quantity that inequality that is called superadditivity that has been understood in terms of volumes, but now it's very easy to also derive it in terms of flows. Okay, let me move to the interpretation now. Not to talk about the interpretation, and in particular of this discrete version that I was telling you about, it's worth recalling that you can also think of ADS or ADS slices in a discretized manner. So one way to think about that is in terms of tensor networks. And what is done normally is to express the wave function in this form. Here the basis states are written in terms of a tensor product of local state vectors. And what a tensor network does is to provide an ansatz for these amplitudes here. Depending on the tensor network, then or on these ansatz, we can have different structures, different types of tensor, different contractions, and so on. Here, I just want to give you a simple example that will be useful to illustrate what I'm going to say in terms of threads. This simple example is what is called as MERA, or multi-entanglement renormalization ansatz. It's a tensor network that is useful for to discretize the ground states of systems with conformal symmetry. So it was proposed by Vidal a couple of years ago. And in this simple network, what you have is a network in terms of layers, and you only have two types of tensors, the so-called isometries and the disentanglers. So the isometries are physical degrees of freedom, and what they do is to combine a subset of the degrees of freedom. So this combination can be interpreted as a coarse graining. And if you only assume that these are the only type of tensors, then it turns out that it is not enough to capture some aspects of the state. Instead, you need to introduce another type of tensor, that is the so-called disentanglers. These are not physical degrees of freedom. Instead, they represent unitary operations acting on a subset of the degrees of freedom. And the role is to evolve the state in one of the layers to a less entangled state at the next layer, right? So in the continuous version, these are the operations that generate the evolution in this emergent direction, R, the holographic direction. And well, it is natural here because this type of networks was in principle inspired by real space renormalization group, which is captured by this emergent direction in holography. Now, what I want to point out here is that CV duality was originally inspired by thinking about tensor networks in ADS. In particular, if you go to the original paper, you can see that their intuition was that you have a tensor network discretizing a slice of ADS, and then the idea was that the tensors in this network, or the physical tensors, occupy some finite volume, and then the complexity is given by the how big is the this network that I need to describe the state. So in other words, how many tensors? So if you think that the tensors have a finite volume, then counting this number of tensors will give you a notion of volume in the space. Now, combining this with our notion of complexity in terms of these Lorentzian threads, then we can combine these two intuitions. So these Lorentzian threads are also referred to as gatelines. This is some notation that was introduced by Matt and Veronica in their paper. Now we can think of these threads to actually pierce to physical networks, to physical tensors in the network, and we can imagine attach a unitary operation now such that it now connects to sources to the physical tensors. So these unitary operations will act now similar to these disentanglers. And in a continuous sense, it will generate the evolution now in this new coordinate that we are introducing here, that is, in this case, the Euclidean time. One aspect of this picture that immediately arises is that it suggests that at least CV is it suggests that that at least in holography we can act with mostly commuting gates, and by commuting I mean that they don't connect multiple degrees of freedom. And here I just want to emphasize that this is the equivalent version in Riemannian bit threads, is that in holography there was this conjecture that holographic states can be built mostly with building blocks that are basically they just connect pairs of degrees of freedom. This conjecture was shown not to be true. So in general, holographic states, some all holographic states need multipartite entanglement, but there are ways to go around this and then to incorporate these multipartite links in the language of threads. So I'm going to come back this in the outlook, but just at this level, I wanted to emphasize that this reformulation suggests this this intuition of mostly commuting gates. And then the final comment that I want to make here is that since I'm doing this extension to this in this Euclidean, this extension to the tensor network picture to this Euclidean section, then I can think of analytically continuing this to real time, to go back to real time, and then these are these unitary operations that we introduced are the ones that generate the evolution in real time. So in this context, then we can understand the time as to be as an emergent concept in the same sense that as in normal tensor networks, we can understand the Raya direction to be emergent. Okay, so now I want to tell you about this application that we made, is that to relate or to derive Einstein's equations in the bulk from the laws of governing variations of complexity. Okay, and in order to do that, what we did first is to reformulate the flow prescription in terms of the differential forms. So here we just use the map between vector fields and d-1 forms, and in terms of these forms, I can write the flux minimization in this way. Okay, then the next step is to develop a notion of perturbative Lorentzian threads or Lorentzian flows. And by this, I mean, I'm imagining that my my state is just a small perturbation over my target state is a small perturbation of the reference state, and in that case I can no, sorry, I imagine perturbing the background, a given background. Okay. In that context, then either in the language of vector fields or forms, I can also develop a perturbative expansion, and I can encode the variation on the complexity either by a small variation on the vector field or the form. What we realized in our work is that using covariant phase space techniques, that we can come up with a very natural candidate for this object, this perturbed form, in terms of this what is called the bulk symplectic current. The bulk symplectic current is defined in general in this way. So this theta here is the symplectic potential, and these deltas here are arbitrary variations. So the symplectic potential arises in arbitrary variations of the bulk Lagrangian, is in particular in this second term. The first term is just the normal term encoding bulk's equations of motion, and the second term is just a boundary term. Now, this bulk symplectic current, it perturbatively, it solves the minimization problem. But here, I just want to point out that in the context of holographic complexity, this is not the first time that it comes out. There is this set of papers by these authors that already use the bulk symplectic current to define complexity. And what is useful for us is that the bulk symplectic current defines a first law of complexity when the sources are deformed via the New York transformation. So I'm not omitting the technical details here for simplicity, but for a particular transformation, then you can write down a first law in which you evaluate the bulk symplectic potential in the slit of the Euclidean manifold, and that gives you the change in complexity. And on the other hand, you can evaluate it at the bulk symplectic potential. You can evaluate it at your surface sigma, and that gives you the change in volume. Okay, so this in this sense, it gives you right away the first law of complexity. What the key point here is that this form, this omega, this is closed whenever the bulk satisfies the equations of motion. So whenever you have you are on shell, this form is closed. So you can use Stokes' theorem to rewrite, instead of doing these surface integrals, you do now a volume integral in one of the Euclidean portions of the manifold. And you can write down what this integral is, now with the exterior derivative of the form. And it essentially gives you this difference. So this is an off-shell relation, but now assuming that the state satisfies the first law of complexity, then what you get in the left-hand side is an integrated version of Einstein's equations. So this is maybe familiar for some of you, which who are familiar with how Einstein's equations are derived from entanglement entropy. And in that case, what you need to invert the problem and recover the full Einstein's equations instead of an integrated version is to consider all possible regions and different time slices, for example. In this case, it's something very analogous. So here, what we need to do is to demand that the first law is valid for arbitrary initial Lorentzian data. So what you do is to deform the integration contour to allow for a little bit of real-time evolution. And now you can demand that the first law is valid for data, initial data defined over slices, not only sigma, but other slices sigma prime that are either boosted versions of the original, or you can add time translations and so on. Once you go back to Euclidean signature, so these boosted slices, now they correspond to other cross sections of the Euclidean ball. And just by demanding that the first law is satisfied for all of these configurations, is that you can invert this problem and recover essentially the linearized Einstein's equations everywhere. So this is a nice result, and then this shows that indeed Einstein's equations emerge covariantly from the laws of complexity. Okay, in the last part of my talk, I just want to share some thoughts about complexity equals volume in general. And here, what I wanted to emphasize. So we were thinking about if it makes sense, if complexity volume makes sense, in the sense that if this optimal network defined on the maximal volume slice is sufficient to characterize the complexity of a general state. So we thought about it, and then we came with an argument to say that that it is not enough in some cases. So the observation here is that if you only have access to that tensor network, then in a general state, that tensor network is not enough to compute a subset of the observables in the state. One of such examples is the entanglement entropy. In particular, if I'm studying a dynamical setting that is evolving in time. Instead of a minimization in the bulk, what you now need to use the HRT prescription, where instead of the minimization, you have an extremization. Or equivalently, you can rewrite that problem in terms of the so-called maximum prescription, where you now fix an arbitrary slice sigma, then you find the minimal area within that sigma, and then you vary over all possible sigmas, and then find the maximal volume. So the same formula or the same prescription have an equivalent version in terms of tensor networks. But from here, you can already see that if you only have access to one of the tensor networks, then it is not enough to consider all possible entanglement entropies in the subsystem. Here, the important point here is that the maximal it is not true that the maximal volume slice can in general be foliated by HRT surfaces, right? So the HRT surfaces in a general time-dependent state, they do not need to lie on one single slice, nor the maximal or not any slice. They just span over all different portions of the width patch. And then it is clear from this perspective that if you only have access to one single tensor network, then that would be insufficient to characterize the full state. Okay, so likewise, then what we said is that, okay, if you only have access to this network, then counting the number of tensors, or just defining a complexity for this network is not enough to characterize the full state. So instead of that, we proposed an alternative or an augmented version of this, in which we now consider not only the optimal one, but we now consider all possible tensor networks on all possible different sigmas. And then we can define now complexity as some notion of average quantity that emerged from considering all possible tensor networks, right? So, of course, this proposal is not complete in the sense that we are not defined, have not defined what this weight is, or even what this measure of integration is. Depending on that, you can decide what slices contribute and how much they contribute to this notion of complexity. Likewise, we have not defined explicitly what this control parameter is, h bar, but we introduce it here thinking that in some cases, the saddle point approximation should be valid, right? So if the saddle point approximation is valid, let's say for static cases, then we should recover. We were thinking that we should recover in a saddle point approximation, we should recover the CB. In those cases, as we know, the maximal slice is indeed enough to compute these observables. So it's natural to conjecture that in a saddle point approximation that we should approach to that limit. So we were thinking that h bar might be related to a time scale of the state. We have not attempted to make this proposal more to push it forward, but I think he would be interested to see if this notion of more generalized notion of complexity can be related to, in principle, other proposals in holography, for example, CA, or even with path integral optimization, which is written in a very similar language as this ensemble, this path integral average. There are a number of follow-up ideas that we are thinking about. One of them is to develop, or if we were thinking if it is natural to, if it makes sense to define a Lorentzian version of these multiflows. So multiflows are a set of flows that were crucial to prove, in the Riemannian case, they were crucial to prove the monogamy of mutual information. So we're thinking if it makes sense to define them in the Lorentzian case. And if so, what would be equivalent of these higher order inequalities? Similarly, as I said, this reformulation suggests that the gates that you need are mainly commuting, but as I said, there are proposals for generalization of bit threads that account for these multipartite entanglement contributions. And it would be nice to now try to come up with a Lorentzian version of these proposals to now generalize or to account for possible gates that are non-commuting, in the sense that they might connect different degrees of freedom. We are also trying to push this proposal forward of deriving Einstein's equations, trying to see if at least perturbatively you can go beyond the linear order, or even maybe in the context of double holography, maybe it might be a way to go beyond that. Finally, we are thinking about topics about bulk reconstruction. So in particular, thinking that these threads, for example, in a two-sided black hole, even though the maximal volume slices, they do not reach all the way to the singularity. The threads, the Riemannian Lorentzian threads, they reach the singularity. So we were thinking if just by understanding the dynamics, we can come up with a way to reconstruct the state very close to the singularity. Yeah, and I think I conclude here. Yeah.
Thank you, Juan, for the very interesting talk. I think we have time for a few questions.
Hi, Juan, I have a question. Hello, can you hear me?
Yeah.
Okay, so thank you for the nice talk. So if you have I have the question that if you have two disconnected regions in the boundary and you can change the size of these intervals, then you can have a non-trivial entanglement wedge, right? And so you can have a, you can compute the volume using the bit thread, the description that you have mentioned. So I was wondering if you have some unique version of proposal for computing the entanglement wedge cross section, because there are different versions of entanglement cross section dual to the boundary, right? So can bit thread be an unique prescription to
yeah, so there are already a couple of papers that deal with the entanglement wedge cross section. So one is by Matt, another one by Bao and company. And yeah, so they have concrete proposals to compute the cross section and actually to interpret what it is actually computing.
Okay. I mean, using this the volume proposals that you have just mentioned here.
No, the volume is for the Lorentzian case. So their work is in the Riemannian case. It's purely Riemannian. So.
Oh, okay. I see. Okay. Thanks.
Hi, I have a question.
Yes.
Hello. Yeah, nice talk, Juan. Thanks. I guess my question would be that wouldn't one expect there to be some interactions between these threads? Is it not reasonable to think that there should be something?
Yes. So that's exactly this point here, that maybe there is a generalization that now, so this picture that I showed you is individual threads. They are kind of individual and they don't talk to each other, right? So that suggests that the gates that I'm allowed to act with, they are just commuting gates. But you can think of generalizing this such a way that they do talk to each other. And that's in the Riemannian context, that extension has been developed already. And it is, I think it's interesting to ask if there is a Lorentzian analog to those constructions.
Okay, and I guess another question along similar lines would be that when you have these one-dimensional surfaces, right? I mean, that's what these threads are. Can they not like braid and twist around each other and have some non-trivial topological structure in that?
Yeah, I think they may have twist and cross each other, and I mean this one of the features of this reformulation is that the solutions that maximize or minimize the flux, they are highly non-unique. So you can deform them in different ways, and they can twist around, or yeah.
So what is the statement of diffeomorphism invariance in this picture?
Well, so far I'm thinking of having a fixed manifold, a fixed background, and so if you're asking the question about if this non-uniqueness might be associated to that, I think that not directly, at least, because even if when you completely fix the gauge or your set of coordinates, there are already high level of non-uniqueness.
Okay, so that non-uniqueness you're saying might be.
Yeah, so in the Riemannian case, the non-uniqueness, the way I understand it is that you are allowed to act with unitary operations in the region of interest, and that doesn't change your entanglement entropy. So you can move degrees of freedom around or swap them and so on. And I interpret that in that way. But yeah, diff invariance, I don't know how to. I think that would be something extra.
All right. No, it's just some food for thought. And my apologies for the audio disruptions from the background. It's unavoidable in some circumstances. So yeah, that's just family. Anyway, thanks for.
Okay.
More questions? I can ask a very quick one. It was, I think I missed exactly how the reference state enters this construction. Because if I understood correctly, I mean, you reproduce these properties from the volume proposal, but then at some, I mean, how do the bit threads know about the reference state? That was not really clear to me. Could you explain that again?
Okay, so I can explain it at this level of this solution of using the bulk symplectic current and there. So first, it's important to realize that for this reformulation to work, you need this Euclidean section here. Also one in the picture, but I can forget about the one in the picture and just focus on this. The reason is that because you have a divergenceless, the flux is conserved, so I can forget about this part and just focus on what is in the past. But the way that this enters is that I'm saying that these threads now are attached to the sources here. That the sources that you need to turn on from to bring the reference state into the target state. And if these were absent, then I could collapse this part to a point, this state, and then the slice would have a zero volume, or I could fit zero threads in that. At the level of the bulk symplectic current is more clear because this New York transformation is such that it precisely deals with deforming the sources in your field theory, no? Right? So the sources, I mean the non-normalizable solutions as they approach as in this Euclidean part. Right. So basically, this New York transformation is already a solution at the linear level of the problem of state preparation. Right? It tells you how via Einstein's equations how a reference state with some sources evolve into a given target state.
Okay. Okay. Yeah. Now it's clear. Thanks, Juan. Maybe we have time for one or two more questions.
Yeah, I have a question. So in your last slides, you mentioned there is some direction to probe the black hole interior by using this thread, right?
Yeah.
So somehow I have a little bit problem to visualize it. Like I thought those threads are either, if in Lorentzian case, they're like time-like, they are following a time-like trajectory, right?
Yes.
But if you enter inside the black hole horizon and then go out somehow, that's not really following the time.
No, they enter and they end up at the singularity. So you can imagine a version like this for a black hole. So it's the equivalent is like preparing the state using the Hartley-Hawking method, the path integral, and then you replace the past by an Euclidean manifold that is used to prepare the state, and then there is a Lorentzian evolution that ends up at the singularity. Right, so then these threads will emerge from the Euclidean section, and then these are word lines, the time-like word lines that just start at this Euclidean section, and at some point they will probe the region close to the singularity and then hit the singularity.
Yeah, so my question is that I thought that the threads really carry some information, but when they hit on the singularity, in this case, like how are we able to read out this information they carry down?
Well, that's part of the problem now. So, but I mean, I just don't want to say anything about the moment at which they hit the singularity, because I mean, you need quantum effects to even talk about that. But you can probe the region very close, right? Up to the point where the curvature is flanking. And that's already more than volumes can probe now, because if you remember, if you compute volumes, there is a region that cannot be probed at these volumes. That is not small, it's kind of large, parametrically large.
Okay. Yeah, probably it's still something working in progress. I see. Thanks.
Anyone else? If that's not the case, then I would like to thank Juan again for the very interesting talk. Thanks, Juan.
Okay.
I was
Thank you for the invitation.
Okay, so in theory, I stopped the recording now.